Good morning, everyone. We start the first session today, the session number 9. The first presenter will be Zbynek Cerman. The title of this is the transfer stable aggregation functions. Is
Thank you for the introduction. Today, I would like to talk about my main research, which is property transfer stability. So my presentation is divided to these 4 sections, where the first 2 sections are quick introduction to my research. So you will know it. And another 2 section, we show 3 examples for application these aggregation functions. So like I said, because of time, we very fast skip the introduction. So lattice, the first one, general lattice with the smallest and the greatest element, where for the each 2 elements exists supremum and infimum. Another is chain, and another lattice is the so-called n-dimensional diamond. So in this case, it's 5 n-dimensional diamond. So all elements are incomparable. Now, it is clear that in lattice, we can measure distances between 2 elements. So the distance between 2 elements is the number of edges. So we have the least distance with the small d and the greatest distance with the big D. So the least distance and the greatest distance. And for me, the distance stable lattices are very important because in these lattices, for each 2 elements, the least and the greatest distance between each element is the same. So we can see this is distance stable lattice and this not distance stable lattice. So now we all know aggregation function, so I can skip it. Okay, binary aggregation function on 4-element chain. But this is main property of my research, which is transfer stability. And this property said that if we have 2 inputs, and in one input, one value move up and another value move down by the same distance, the result of the aggregation function is the same. For example, the arithmetic mean is transfer stable aggregation function. Okay, based on this definition, we can divide all k-tuples in the lattice to the classes where 2 k-tuples belongs to the 1 classes if for all transfer stable aggregation function they have the same results. So for example, these are all classes for binary aggregation function on the 4-element chain. Or these pictures show all classes for binary aggregation function on 2-dimensional diamond. And like we see, all classes are linearly ordered. But not always. Exist lattices where the classes are in zigzag order, but we don't want these lattices. So the new class of lattices is transfer stable, where all classes are linearly ordered. So for example, this is distance stable lattice, so of course transfer stable. This is not distance stable lattice, but it is transfer stable, like we see on this picture for binary aggregation function on pentagon. So the classes are linearly ordered, and this lattice is very bad because it is not transfer stable. Now, the main results of my research. So I show you 3 examples of application this function. So you all want to buy laptops, right? So we buy 3 laptops and we have these 4 parameters divided to these categories: price, weight, graphics cards, and operational RAM. And based on these parameters, we can divide to the chains. So for each parameter, we create chain. Chain is distance stable lattice. So now we create direct product of these lattices, and we get lattice L with 336 elements. This lattice is, of course, distance stable lattice, because direct product of distance stable lattices is distance stable lattice. This lattice has depth of 14, where depth is the distance between smallest and the greatest element in the lattice. And if we want to buy 3 laptops, we use ternary aggregation function on this lattice, and we get 43 blocks, so-called qualitative classes. For example, this laptop with total distance 9, because we sum this distance in chains, and this laptop has total distance 9 only in the lattice L. So we have to choose 3 laptops to get lattice L23. Okay. So for example, if you choose 3 these laptops, you get to the class 0 in the lattice L23, and this class is of course best to the seller. Yeah, this laptop is very expensive. On the other hand, these 3 products belongs to the class 42, and these laptops are best for us because they are good and they are cheap. But there is a problem, because these laptops doesn't exist, so you cannot buy it. Okay, so this class is unavailable. Never mind. Now we want to agree with the seller to the so-called golden mean. So this is qualitative class between 0 and 42, which is good for us and good for seller. So for example, 29. That means you want choose 3 laptops with the total distance of 29. For example, these 2 laptops has distance 9 and 10, and these laptops has distance 9, so total is 29. This means this trio of laptops belongs to our qualitative class 29. Okay, but like I said before, unfortunately, qualitative class 29 is unavailable. Why? Because there is no laptop which exists. Okay, so the smallest class is 0 and the greatest class is 42. And now we find the highest available class where there is laptop which we can buy. So that means this laptop with distance 9 exists. So if we choose 3 of these laptops, we get to the class 27. So this is available class. On the other hand, these 3 laptops with the total distance 3 3 these laptops belongs to the class 9. So this is smallest available class. That means there is no product with the total distance 10, and there is no product with the distance 2. Okay, so we now to find new golden mean between 9 and 27. For example, golden mean is qualitative class 15. Okay, and now it's up to you. Choose 3 laptops with a total distance of 15. For example, these laptops belongs to the qualitative class 15. These laptops exist, I hope, and you can buy it. Okay. This slide show list of several laptops which exist. So it's up to you. Choose 3 of them with the total distance of 15, and you can buy it. For example, these are potential purchases. And for example, if you want choose laptops according to the price, that means, for example, the price should not exceed 4,000 Czech crown. You can choose this trio of products, this trio of laptops. Another, if the weight should not exceed 5 kilos in total, all 3 laptops should not exceed 5 kilos, you can choose option 8. Another, you want free game playing graphic cards, you want to play games in the school, why not? You can choose option 2. Or you want total size of 3 laptops should be greater than 80 gigabytes. Okay, you can choose option 2. Another example. So again, we want to buy 3 laptops, but with new parameters: operating systems, brand, display type, and display size. Again, for these parameters, we create chains, and we get direct product of these chains, lattice P, with 126 elements. It is distance stable, of course, has a depth of 11, and for 3 laptops, we use ternary aggregation function, and we get 34 blocks. Okay, so we get that these laptops is the worst, and this laptop is the best. Okay, if you hate Apple, you are happy now, right? But this is not real situation. Okay, we have problem. That means that we, instead of chains, we use n-dimensional diamonds where these parameters are incomparable. And moreover, 0 and 1 are unusable parameters. So we don't want laptops with these parameters. And direct product of these n-dimensional diamonds, we get again distance stable lattice U with 900 elements with depth of 8. And for ternary aggregation function, we get 25 blocks. Based on real situation, we get only one reasonable qualitative class, which is 12. In another classes, there is no real laptop. So golden mean is, of course, 12. Yeah. And for example, these are laptops with distance 3, 0, 1, no, we can use it. Laptops with distance 5, again, 0 and 1, no, there are unusable parameters. And only in the laptop with distance 4 exist, but not all. There is laptops this, but this is not real laptop. Okay. Yeah. So you choose 3 laptops with distance 4. So this is trivial example. That means, for example, this trio of combination of laptops is problem because there is laptop which doesn't exist. So no. This trio of products again doesn't exist because this laptop and this laptop doesn't exist. And again, these free laptops exist because all free laptops we can buy it. So this is potential purchases. Okay, and the last example, again, and we mix together. So again, we want buy free laptops, and we have parameters, operating systems and brand, which are incomparable parameters. That means we have used two-dimensional and seven-dimensional diamond. And the another parameters, weight and types of graphic cards are comparable. So we used two-element and three-element chain. Okay, we create direct product of these four lattices, and we get lattice R with 216 elements. It is distance stable, of course, with depth of 7. And for free laptops, we won't buy it. We use ternary aggregation function on this lattice, and we get 22 blocks. Okay, there is problem, so we find available classes. The smallest classes is this, and this laptops doesn't exist. Okay, so that means the smallest available class is 6. These free laptops we can buy, so this is smallest available class. On the other hand, the highest available class, 21. These laptops doesn't exist, so we won't buy it. But these free laptops, we can buy it, so the highest available class is 15. That means the original range for finding golden mean is between 0 and 29, but real range is between 6 and 15. So that means we agree with the seller, for example, on the qualitative class 11, and it's up to you. Choose 3 laptops with a total distance of 11. For example, this one represent qualitative class 11, or this one. And last remark, you now know it, that for free products, we need 11 points. And one incomparable parameter costs 1 point. So that means for 2 incomparable parameters and free products, we cost us 6 points. So 5 points left for comparable parameters. Okay, you want lightweight laptops, so you can choose 3 points for weight parameter, and you can choose this trio of products or this trio of products, and it's up to you what laptops you choose. Or you can use all 5 points to the graphic cards, and we get in this case that there is possible purchase with 2 game playing graphic cards and 1 dedicated graphic cards. So for example, you can buy this trio of laptops or this trio of laptops. Okay, that's my references, and that's all, and thank you.
Thank you very much for your presentation. Any questions, remarks? If there is no questions, thank you very much.
Thank you.
Okay, the next presentation will be given by Martin. There is construction of uninorms on the unit interval from T subnorms and or T superconnorms.
Thank you. So, motivations for this research were these two papers. The first paper is on the ordinal sum of unions, and the other paper is in fact a starting point for this research that I will present now. So we will construct a union that will have a neutral element somewhere between 0 and 1. Gamma sub E and gamma upper E are sets of idempotent elements of this union mu. Each of them contains at least 3 elements. This means always 0 neutral element in this first class is of course inside, but there is at least 1 idempotent element in this interval, and also in the interval E1 is at least 1 idempotent element. And these sets are indexed by these two sets, N and M. This means this gamma sub E has n element and intervals between these idempotent elements, and the other set has m intervals between those idempotent elements. And these are these intervals in this within this 0E interval. The idempotent elements are denoted by alpha, and in this interval E1, the idempotent elements are denoted by beta, and the indices go downwards. And these two sets, theta I and Cj, will denote always all elements from this interval I or Jj. And this probably not correctly written. This denotes that when we are near 0, no interval contains minimum when we construct this p-norm part, and also when we are near 1, no interval contains maximum in this t conorm part. This will be important. So this is our case. For simplicity, here I have just 3 subintervals, and also here just 3 subintervals. So we have here 3 T subnorms, and in this part 3 T superconorms, and each of these T norms has this alpha I as idempotent element, and here this beta are idempotent elements. And now we have here 2 lemmas that say something on the properties. Maybe better when I go back to the picture. The first lemma says that when we find here in this rectangle at least 1 point where the value is less than the neutral element, then we have in this whole area only values less than the neutral element. And the other lemma says that here this idempotent, this means here we have this segment is constant, and it must continue also in the upper part when we have here elements less than is. This means in these segments we have only these values alpha 1 and alpha 2. And this means also that in this part, when we are here within this subrectangle, then we have there only elements from this interval alpha 1, alpha 2. And these values, when we are within the open interval with one input, then the values must be also from the open intervals, since otherwise we would lose either monotonicity or associativity. So, and of course, dual lemmas can be formulated for the column when we have there one element greater than the element. So, and this is how we can construct the T subnorm and a kind of ordinal sum of these T subnorms. These F are functions defined always on the F sub I are functions defined on this interval I sub I in this way. This means F at X is this T subnorm I defined here in this on this segment. This is this F2, the values on this segment, F1 and F3. This is of course minimum, because otherwise this wouldn't be a T norm. Oops. And of course, when we change as values on this here for one, then we get a P norm out of this T subnorm. So this is well known. So this is just notation for this ordinal sum of T subnorms and dually for T superconorms. And now we proceed to construction for uninorms. So we will have here 3 T subnorms and T superconorms. In this part, we have just values from this interval 0, alpha 1, and they are defined by these values on the segment. This means here when we choose this segment that is perpendicular to x-axis, this is the values there are just constant, and also here in this part, and then here this part, this part. When we choose one T subnorm and one T superconorm, I is T subnorm, J is T superconorm, then on this set, this interval, neutral element, and the other interval for the superconorm, we can construct a uninorm. This is denoted by this U sub I and upper index J. And the restriction to this part, we will have here a function G sub I. This means when we have, say, T1 as 3, the U1 3 union. This means we are here in these two rectangles. Then here we have again a function G sub 1 and upper index 3. And now, when we want to construct a union from this faucet, then we can choose we have several possibilities to choose from. First possibility is that we couple T1 S1, and here we give values from this union part. Here we have T2 S2, and in this upper part we have values defined by this function g sub 2 and upper index 2. This means these segments perpendicular to x-axis are constant, and here again, here we have constant, but it goes up to 1. So this is one possibility, and this is similar to the ordinal sum of p-norms and of unions, standard unions constructed from t-norms and t-conorms. But we may have also this possibility that we couple T1 S3, T2 S2, and T3 S1, and then here these segments are constant. These segments are constant, and in this part we have minimum. We may have also this kind that we couple T1 S1, but also T3 and S1. This is also possible when this is a proper T subnorm. And then here we have minimum, and in this part we have again these segments constant. And now one example how it may look like. So we have a neutral element 1/2, alpha 1 is 0.2, alpha 2 0.3. So these are these idempotent elements within this interval 0, 1/2. And in this interval 1/2, 1, we have idempotent elements 0.9 and 0.7. The T subnorm T1 is 0 in this square 0, 0.2. This means it is a kind of drastic T subnorm. Just here we have 2 values on this interval 0. In fact, 3 values. On this interval 0.1, 0.2, we have value 0.1. At this point, we have value 0.2. And when one input is less than 0.1, then we are here in this situation. So there is the value 0. T2 is again a kind of drastic T subnorm, and T3 is just minimum. T superconorms. We have again S1 is a drastic T subnorm. S2 is just standard Lukashevich T conorm, and S3 is maximum. S3 is drastic T norm. Yeah, drastic T conorm. Now, so this is this T norm part. Here are these values. T conorm part, but yeah, here is a mistake. I constructed this for the case that here is maximum. So I'm sorry for this mistake. So if here we have maximum, then in this part we have minimum. In this part maximum. This means in this part we have x, in this part we have y. Minimum, those cases, here we have maximum. And one possibility how we can define values in these three rectangles is that here we have, in fact, copies of this Lukasiewicz T norm. Here's this triangle. So this is a constant triangle, and here are those level set functions which are parallel to this segment. And here in this part, we have an area of constantness, three areas of constantness. These always, the values are smaller than here, these values. And this is because all values here must be less than values in these segments. Otherwise, we would lose the associativity. And this means here, this tiny strip is, in this tiny strip, we have, again, minimum. Of course, the one here. And we could play with this construction. We could change. We could here we could give just minimum and cut in the upper part this in fact image of this plastic, and then there are still several possibilities how to couple this. Okay, so this is all I wanted to show you. Thank you.
Thank you very much. Any remark, questions? I have one question connected with the construction. If you take the ordinal sum of these subnorms, in fact, you use idempotent element of this subnorm, yes? But in fact, in this point, you can have no idempotent point, yes? Yes, but it's always is needed to be here the idempotent point.
Yes.
Because for okay.
Otherwise, here this point.
This is connected with this, yes. That's yes. There is left closed interval. Everyone.
Yes. Yes.
Okay. Thank you. Any more questions? Remarks? If not, thanks again for the interesting presentation. Thank you. The next presentation will be online. That will be given by Andrea Meszarowa-Zemankowa, and there will be about the construction of idempotent norms on the bounded lattice.
Thank you very much for this introduction. Greetings from Bratislava, and let me just share my slides. Okay, can you see it? Okay, I hope it's working. Is it okay?
No, it's okay.
Okay, thank you. So, ladies and gentlemen, in this talk, we have a very important mission because Cinderella asked us for help. Some time ago, she wanted to go to a ball, or some say that it was a nice conference. I don't know exactly. But her evil stepmother, which was also very sly, told her that she can go only if she can determine all idempotent uninorms that can be defined on a bounded lattice that she will give her. Luckily, Cinderella was clever, so instead of calling her DAOs, she called our institute and she asked us for help. So as a First step, we collected all basic facts that we know about idempotent uninorms. So we will work on a bounded lattice L, and uninorm on L is a commutative, associative, and monotone function, which has neutral element. We also know that uninorm is idempotent if aggregation of any two equal values is again the same value. It is also quite well known that if the neutral element is equal to the top element of our lattice, then we will obtain a T-norm, and there is only one idempotent T-norm on any bounded lattice, which is just coincide with the mid of our lattice. Similarly, if neutral element is equal to the least element of our lattice, then we obtain a T-conorm, and the unique idempotent T-conorm is the one which coincides with the join. And therefore, the only interesting case is when neutral element is different from both boundary points. When we will describe our uninorm, we will talk about several important parts of our lattice. So lower interval will be interval 0e, upper interval will be interval e1, incomparable part will be the set of points which are incomparable with neutral element, and averaging area is the product of the lower interval and the upper interval and its reflection. We will use results of the following two papers by Kiley, Carousel, and Messier, and Kiley and Rigash, which show several interesting properties of idempotent uninorms. But let me show you where is our main problem. Each idempotent uninorm is commutative, associative, and idempotent. So even without monotonicity, for each such function, we can define the following relation, that x is smaller or equal to y if aggregation of x and y is equal to x. Then this relation is a partial order, because reflexivity follows from the idempotency, antisymmetry follows from the commutativity, and transitivity follows from the associativity. So each idempotent uninorm corresponds to some partial order on our set. And also in the opposite direction, taking any partial order that defines a mid semilattice, then the corresponding mean is commutative, associative, and idempotent. So from this, we see that the only problem in this characterization is the monotonicity. Or alternatively, we can say the compatibility between our lattice order and this U order. For example, in the simplest case, when we work on a chain, then from results of Strogawa and Drevniak and others, we know that each idempotent uninorm defined on a chain is internal, which means that aggregation of any two inputs is one of these inputs. And in such a case, our U order is linear. Therefore, it is not surprising that each idempotent uninorm defined on a chain can be expressed as an ordinal sum of trivial semigroups with respect to this U order. And also in the opposite direction, taking any linear order on our set, we will obtain a commutative, associative, and internal function. But how it works with this monotonicity? In the case of a chain, it is quite simple. We need only two conditions, that our trivial summands, which correspond to points that are smaller than neutral element, are ordered in the same way as these underlying elements, and trivial summands which corresponds to points that are bigger than neutral element are ordered reversedly to the order of these points. And that is all. We don't need any other conditions. If these two conditions are fulfilled, the monotonicity is ensured. So it works like such two comps which are arbitrarily put together, and this linear order ensures monotonicity. But let us go back to our problem, how to help Cinderella. Luckily, we observed that the stepmother was also very lazy, so she selected the lattice where all points were comparable with the neutral element. And therefore, we decided to solve this problem generally, to characterize all idempotent uninorms that are defined on bounded lattices where all points are comparable with the neutral element. Okay, from the two papers that I mentioned, we know that in this case, we have only three possibilities for our inputs. Either both belong to the lower interval and our uninorm coincides with the mid, or both belong to the upper interval and our uninorm coincides with the join, or our inputs belong to the averaging area, and in such a case, our aggregation is internal. So we see that the only thing that we have to do is to characterize our uninorm on the averaging area. Because the question is, how can we select between these 2 points and preserve properties of a uninorm? Because in this case, it is a bit more complicated than on a chain. And I will immediately show you why. From paper of Kiley and Rigash, we know that if 2 points, for example, in the upper part, are incomparable, then if we aggregate them with any value from the lower part, we have only two possibilities. Either all of these three aggregations, whether we take x or y or aggregated value of x and y, are equal to the corresponding point from the lower interval, all three of them are equal to the corresponding point from the upper interval. And of course, the same holds if our incomparable points are in the lower interval. So this shows us that incomparable points and their aggregated values are somehow dependent, or we can say tangled together. And then uninorm on these points take similar values. So the question is clear. How can we sort points of our lattice into sets where we will collect all points that are tangled together, and how to determine which points are independent? And for this, we have defined very useful function inc, which will assign to a set, a bigger set, which will contain also all tangled points. Since all points from the lower interval are comparable with all points from the upper interval, it is enough to talk only about the following subsets. So if our set S is a subset of the half-open lower interval, then inc of S will be union between S, all points that are incomparable with points from S, and the set of all meets between S and IS. If S is a subset of half-open upper interval, then inc of S will be union between S, IS, and set of all joins between S and IS. And of course, since neutral element is comparable with all other points, then inc of the singleton E will again be the set which contains exactly one point, E. Some properties of this function is monotone, half-open lower and upper intervals are invariant. And what is important, for each subset, there exists a subset over line S, which contains S, and it is invariant with respect to the inc function. So in fact, what we do, we take a set, and then we add all tangled points, and we repeat this until we reach this set over line S. On infinite lattices, it is a bit more complicated, but we will not go into details. Let us see some example. For example, on this structure, if we start with point x1 and apply the inc function, then we obtain a set which already contains 3 points, 0, x1, x2. In next step, we obtain also x3, then x4 and x6. And finally, we see that starting from a set containing only 1 point, this structure is so much tangled together that finally our set over line S will be whole half-open lower interval. What is important is that the set over line S is closed under meet in the lower interval, and it is closed under join in the upper interval. This means that each such set is closed under any idempotent uninorm. Moreover, if some element is smaller than all points from set S, then it is smaller also than all points from set over line S. And if it is bigger than all points from S, then it is bigger also than all points from the set over line S. This means that our task is easy. We should just focus on each element from our lattice and only see with which points it is tangled together. And therefore, we should focus on sets over line X. Then we can show that for any point which does not belong to the set over line X, points X and Y are comparable, and aggregation by any idempotent uninorm is internal. And moreover, if this aggregation is equal to X, the same holds for all points from the set over line X. And if it is equal to Y, then the same holds for all points from the set over line X. So this is what we wanted, but the problem is that these sets are not equivalency classes. Because if we have some element from set over line X, then either these two sets coincide, what is desirable, that overline X is equal to overline Y, but in two special cases, if Y is equal to infima of overline X in the lower interval or to suprema in the upper interval, then this point is comparable with all points in our lattice, and this means that the set overline Y is just a singleton Y. And that is why we need to take the following sets as X, which is simply the union of all sets over line Y which contain X. And in this way, we can include also this infima and suprema to our classes. So these are already our desired equivalency classes, which are closed under any idempotent uninorm, and we can show the main result here. So under assumption of axiom of choice, we can create a set by selecting one representative from each equivalency class. And then if we take order inherited from our lattice, this Q will be a chain. And what is important, idempotent uninorms on L are then in one-to-one correspondence with internal uninorms on the chain Q. This means that aggregation of any two representatives completely determines whole aggregation on the product of the corresponding two equivalency classes. So we can say that these trivial summands, which we have in the decomposition of internal uninorm on a chain, are here replaced by the corresponding equivalency classes. Of course, we can show this also without axiom of choice. I just thought that this is more illustrative. Okay, so let us go back to this example, what we should solve for Cinderella. What we should do here is just to find our equivalency classes, our tangled points, which are the following sets, which you can see in red. And this corresponds to the following chain. From what we know about internal uninorms on a chain, we know that summand A is always smaller than summand B and smaller than neutral summand. And summand C is always smaller than the neutral summand. And therefore, we see that in this case, we have three possibilities. Either summand C is the smallest from ABC, and in such a case, our uninorm on the averaging area is equal to maximum. Or C is biggest from ABC, and then on the averaging area, we obtain minimum everywhere. The last case is when C is between A and B, and in such a case, on AC, we have minimum, and on BC, we have maximum. Well, so Cinderella had a great time, and her evil stepmother was very angry that she was able to solve this problem. But in a short time, a new ball was announced, and Cinderella wanted to go there again. But this time, her stepmother selected even harder problem. So she selected the lattice where there was exactly 1 point incomparable with the neutral element. From what we know from the two papers that I mentioned, we know that aggregation of any 2 points by this uninorm, it is either equal to the meet or to the join, or we obtain value W, which is this only incomparable value with the neutral element. And therefore, we will divide our lattice into 2 sets. First set is the collection of points that aggregates with W to a value different than W, which means that in the lower interval we obtain meet and in the upper interval we obtain join. And B will be collection of points that aggregates with W to the value W. So I think that you already see that even we have added only 1 point, it is much more complex than in the case when all points are comparable with the neutral element. Okay, we will divide the, okay, sorry, just it is clear that points neutral element and W belongs to the set B. We will divide these sets further into lower part and upper part, and we will also assume points from set A which are incomparable with the value W and which are comparable with W. And then by taking intersections, we will obtain the following 4 sets in the lower and in the upper part. And we will do the same with set B, lower part, upper part, incomparable part, comparable part. And by taking intersections, we will obtain these 4 sets. Now, properties of an idempotent uninorm imply several restrictions on these sets, but I will not go into details because time is running and immediately skip to the values of any idempotent uninorm. So we know these values already if one of the inputs is equal to neutral element or to the value W. And in all remaining cases, we obtain the following. If both inputs belong to the lower interval, then we obtain meet. If both inputs belong to the upper interval, we obtain join. So this is what we already knew before. What can we tell more? Associativity and monotonicity implies that the value W can be obtained if and only if both inputs belong to the set BC and they are from opposite parts. Similarly, associativity implies that if our inputs are from opposite parts and one belongs to the set A and the other to the set B, then the result will be corresponding input from the set A. And finally, if we have 2 points from set B, from opposite part, where one is incomparable with W and the other comparable, the result will be the comparable input. So this is what can be shown quite easily by monotonicity and associativity. So we see that in the remaining cases, we have either 2 inputs where both belong to the set A and they are from opposite parts, or both belong to the set BW and they are from opposite parts. We know that these aggregations are again internal, but similarly as before, we don't know which of the 2 we can select and still preserve properties of our uninorm. But luckily, we can observe that if we omit this point W from our lattice, we will obtain a lattice where all points are comparable with neutral element. And although this set is not closed need not to be closed under our uninorm, still we can use our inc function on this lattice only to determine tangled points, set of tangled points, because also here it works similarly. For example, as I mentioned, if we aggregate 2 points from different parts, one from A and the other from set B, we will obtain the result from the set A. But the same holds also for all tangled points. If we have some incomparable point from set B2, then the result will be the same. Again, we will obtain this point from B2. So we can say that the tangled points somehow mimic the properties of the original set. And the same holds, of course, if incomparable points are also in the not only lower part, but also in the upper part. And if we put these 2 things together, we see that the tangled points can be only in one of parts. Tangled points between set A and B can be either in lower or in upper or nowhere, which means that all points are comparable between these 2 sets. Because simply aggregation of Y and Z cannot be also Y and also Z at one time. And similar relations holds also for these other properties that I mentioned. So from this, we see that the same holds also for all points that are tangled with the set B1, and the same holds also if we reverse our parts. And also we know that aggregation on the set B of inputs from opposite parts, one comparable, other incomparable, gives us this comparable input. And again, the same holds also for all tangled inputs. So by these relations, we are already able to completely characterize our uninorm. But of course, these characterizations depends on several conditions, and therefore we have to split it in several cases. But I will again not go into details and show you just the basic idea without going much into details. So what we will do is that we will divide our lattice without point W into following sets. In the middle, we will always have points which are tangled between set A and B. Here we will have points from the set A which are not tangled with B, and here are points from B which are not tangled with A, and the same in the upper part. Then these sets are already linearly ordered, and we can use ordinal sum for the composition of our uninorm. So as a first step, we will remove these sets I1R and I2R. And either we can do it directly, take this set, and in such a case, restriction of our uninorm to this set is just a uninorm which we characterized already before. Or we have to take also element W, and in such a case, restriction of our uninorm to this set is a special uninorm on a lattice where we have exactly 1 point incomparable with neutral element, for which the corresponding set B contains only 2 elements, neutral element and W. And such uninorm can be again characterized using the inc function, but I will not go into details. So as I mentioned before, tangled points between set A and B can be only in one of the parts. So now we will suppose that they are only in the lower part, which means that this set is empty. So we will continue only with the following sets. We see that in the upper part, there are no more points from the set A. And we will now divide them a bit differently. Here we will take set of tangled points with set A1 and BC1. And here we will have tangled points from BC2. And this is the remainder of points which are not tangled, which are incomparable with W and from set B. And again, we can take ordinal sum decomposition and remove this part. On this part, again, we have a uninorm which we characterized already before. So what left are these two sets. And again, tangled points can be only in one of the parts, which means that we will never have two inputs from the set BW from opposite parts. And therefore, we are already able to completely characterize this remainder. And like this, in separate cases, we can characterize each idempotent uninorm. In the opposite direction, then it is enough to take suitable sets A and B, which of course depends on the structure of lattice, and we can construct any idempotent uninorm on such bounded lattice. Well, we were able to help Cinderella already 2 times, but now we are starting to worry because we heard that another ball is coming, and we still don't know this characterization in general. So if you have some bright ideas, you can help us to get Cinderella to the ball. We already have some partial results. For example, some few things are also in this paper, which was published recently. But of course, the full characterization is still missing. So I would like to thank you for your attention, and any good sorting ideas are welcome. Thank you.
Thank you very much for your interesting presentation. Any remark, questions? I know that in this presentation there is many technical details that it's very difficult to find all these pieces of this technical thing. Pieces. Okay, I have one questions. There is no other questions. If we have neutral elements and the elements W, there are two non-comparable elements. And for these two non-comparable elements, we can take the next element, W1, W2, and we can obtain the diamond lattice for these elements. If all these sets for W1, W2 will be the same, we can obtain similar characterization or not. You think about this or not? Because I think that will be similar.
You mean that we have this n-dimensional diamond lattice?
Yes, but only for neutral elements W1, W2. If we add the non-comparable element for neutral elements.
If I understood that correctly, then it is exactly in this other paper, which deals with commutative, associative, and monotone functions on horizontal sum of chains. Is it so that you mean that you have a lattice which is a horizontal sum of chains?
Yes, but only with neutral element. The rest element will be the same, like in your presentation. But we add to the lattice L non-comparable element with neutral elements. So if we choose only these these two elements, we add the next element, which is non-comparable with this neutral element, but the rest will be the same. We have the same connection between these two.
Yes, it will be similar, but we know that in this case the sets which are incomparable with W and W2 should be one is a subset of another. So it will be somehow one in another. So also these sets A and B for one element and for other element will be subsets. And then we can do the same decomposition, but of course to more parts. Yes, in a finite case, it will work similarly, but still more and more complex. And the problem is in this whole characterization that the smaller is this comparable part and the bigger is this incomparable part, then this neutral element plays smaller and smaller role. And finally, we will end up with the case when this characterization will be equivalent to the characterization of all commutative, associative, monotone, and idempotent functions, so without neutral element. So this is the main problem, that this neutral element has still smaller and smaller role in this characterization.
Yeah, yes, I understand this. Thank you very much.
Thank you.
Any questions, comments, additional? If no, thank you very much for your interesting presentation.
Thank you.
Okay. Now we have some short break.
Okay. No. Okay, I'm just playing with this pointer. So how does it work? Okay. Two. So, okay. Okay. Okay, so thank you for introductions. You have a short break before that, so I hope you have relaxed. And it will be only short presentation. It's a joint work with Andrea, whom you have seen a few minutes ago. And before we will move on. Let's speak about what the pseudo-uninorm is. The pseudo states for that we think a non-commutative counterpart of the uninorm, and otherwise it's basically a known fact. We know that also we can speak about the pseudo T norm and pseudo T norm in the same sense when the neutral element is the least or the highest. So that's that's similar. However, we are more focused on we were more focused on the proper pseudo uninorm, and we were studying the uninorms when the where the neutral element is in the middle of the unit interval. And so the obvious fact that the commutativity, when it's assumed, we obtain a uninorm. No, the wrong direction. The setup, the basic setup is pretty similar to the uninorm. And we can divide the unit square on those four rectangles where here is the E, and we obtain here the pseudo T subnorm, pseudo T norm, and pseudo T conorm in this in these two squares. And the averaging behavior in these opposite rectangles, which are denoted by AE. Moreover, due to the result which is stated in the classic literature triangular norms, in fact, this result goes to Helder. I think it was in 1901, just for the fact that whenever we have an pseudo T norm, which is continuous, or and so on, pseudo T conorm, then we obtain a commutativity. We have assumed that those underlying functions, so both of T norm, both pseudo T norm and pseudo T conorm of this pseudo uninorm are commutative, and hence we have this commutativity inside. Moving on, just a short reminder, as the Clifford sums showed as not a universal tool, but useful tool for characterization of associative aggregation operators such as T norms, T conorms, and as well as uninorms. Since Andrea has characterized them in 2016 by Clifford ordinal sum, our intuition led us to use it as well for the case of pseudo uninorms. What is tricky? I would like to point on the last sentence of this theorem, that the non-commutativity of this semigroup is dependent on the non-commutativity of components. Okay, and it will and we will see that it reduced the non-commutativity of pseudo uninorm a lot. Okay, just a reminder that for the uninorms, those were the possible segments that can yield in the Clifford ordinal sum the uninorm. Just for short, note that the idempotence elements belongs to either the nilpotent T norm or nilpotent T norm, or are in the separate trivial semigroups. No, so let's get to our research. We have started with examining the points of non-commutativity, and we have assumed that both that this inequality holds, and therefore, obviously, we are here. It's not possible since the previously mentioned result, and we have found these facts, that not only that the x and y has to be less and then and the other greater than E. But however, also the values has to be one of them has to be lesser and the other one has to be the greater than E. Moreover, the non-continuity occurs in some sense in X and Y in those points, since it can be shown that for the pseudo-uninorm with continuous underlying functions, in these sections, there is at most 1 point of non-commutativity, and since this inequality holds, it has to be it has to start in some of the points, and it's a point of non-commutativity. In fact, moving. No. Moreover, for each x, there exists at most one y. Yeah. So it's one fact is that it's spawn of the non-commutativity. Moreover, there holds such inequality, and we will see it. It will lead to the fact that those points belong to the characterizing set valued functions of the pseudo-uninorm. Moreover, can be shown that x and y are idempotent points of a pseudo-uninorm. And lastly, but not leastly, since there are idempotent, it has to be x or y, the value. Note that in this case, it's just the projection on the first coordinate, since x the x does not commute only with this y, and otherwise it commutes, or the projection on the last coordinate, and that's in this case, which isn't written there. So we have this setup, and we decided to with some pairs along this characters set value function. And we decided to define a uninorm, just the replacing those points where the non-commutativity occurs by maximum. Similarly, we can choose minimum, and it doesn't matter. And yeah, we have shown that if uninorm, it's basically pretty easy but tedious, and we have found the decomposition of Clifford ordinal sum with those segments that was already mentioned. Yet we know that if x and y does not commute, so we are here, then x and y are idempotent elements. Yeah, they cannot be part of nilpotent segment. They have to be in the trivial semigroup, and moreover, it is possible to show that those two semigroups are succeed each other. So so there is no other semigroups in the order between them. And what do we do? Okay, we just replaced these two trivial semigroups by the one that unites them, and we choose the corresponding projection. Basically, what we found is this. I don't know what should be there inside this question marks, but however, one of the previous theorems. So I will see and later and what we found. So we found what I'm a bit lost. What kind of semigroups has to be there? So we know that's the semigroups that constitute a uninorm and also those of those projections on 2-point sets. Moreover, and the order, because that's important too, we found that when E belongs to some semigroups, it has to be the top element, and it has to be the top semigroup, and also it has to be a neutral element. Otherwise, it will destroy all what we have done. And moreover, the order is as such. Then when we choose 2 points greater than E, then the order should be reverse, and and otherwise it has to be the same. And that's basically what we have done. And thank you for your attention.
Thank you very much for your interesting presentations. Any remark, questions?
You have claimed that this non-commutativity for any x, you will find a point. This is, does it mean that pseudo uninorms are not neither conjunctive nor disjunctive?
Yeah.
Okay.
Yeah.
Okay. This was question.
There will be no problem with associativity in these 2 points?
Yeah, and in fact, since 0 and 1 are idempotent points, there is a possibility to choose that. Only when this is interesting fact. Then when we have a nilpotent underlying function in one of them, then that what we claim then we obtain a uninorm, and it has to be so even conjunctive or disjunctive. However, in general, it does not hold for any pseudo uninorm.
Okay, for me it's surprise because I think always that these 2 points must be fixed. That's any remarks, more remark, questions? Okay, I have one question connected with the index sets you use for the ordinal sum, because in fact in the case if you have ordinal sum for uninorms, you can instead the singleton, you can take the idempotent parts, yes, and you obtain the countable index sets. But here I think there will be problem with this.
We choose this approach since it was more suitable for our for the proofs and for our work. However, there is possibility also to choose the segments where the projection is on some interval, and it's similar. So.
Okay, that's you put idempotent pseudo uninorms in some segments, and you obtain countable.
The projections.
Okay.
In the.
Okay, and the second.
Can I add
no,
something?
There is no
to this?
time for the question. Maybe there is questions from.
No, I just wanted to add to this index set that even in the case of uninorms, you need not to obtain the composition which is countable. There we had such example which was based on a counter set, So it's not always possible to merge all these trivial summands into some idempotent part. So
Okay.
similarly as in the case of uninorms, also here it can be that it's uncountable.
Okay, but for idempotent uninorms, you can use here as one segment the idempotent uninorms in this ordinal sum. And
Yes, but in fact, all idempotent uninorms can be decomposed into trivial elements. So we immediately use this decomposition, and we do not deal with it as a idempotent part, but we decompose it to trivial elements and use it in this decomposition.
Okay.
Form.
Thank you.
Decomposed form.
Thank you very much for your comments. And thank you for your presentations. We finish this session and we have a coffee break. Thank you very much.